My name is Robert Sloan, and today I will be presenting my work on vision-guided automation and assistance. The goal of my project is to develop a vision pipeline that can locate and recognize objects in a variable workspace for use in automated and assistive tasks. For automated pick-and-place tasks, the placement of the object before being picked up must be very precise. The addition of vision reduces the need for such precision since the position and orientation of the object can be estimated from a point cloud generated from a depth camera. Deep learning can be used to recognize different types of objects, allowing the robot to be used for more complex tasks. In assistive tasks, where the robot is interacting with the human, vision allows for more flexible interaction rather than having a few preset actions the robot will execute. For example, with vision, the user could use a visual cue to request the robot move an arbitrarily placed tool to a different arbitrary part of the workspace. Without vision, the start and end positions of the tool would be limited to preset positions, and another interface would be required to activate the robot. Due to the remote nature of my internship, the project is done entirely in simulation using the simulation and visualization software Gazebo and RViz through the Robot Operating System, or ROS. The simulation environment was set up to be representative of a glove box environment found in the lab. For the robotic manipulator, existing robotic systems in the lab were simulated. The Motoman SIA 5D arm with a robotic 85mm gripper attached as the end effector. Surfaces were added to hold the objects being manipulated. The objects were selected to be representative of the shapes of objects found in the glove box. At the moment, the objects consist of simple shapes like cylinders and cubes, but more complex shapes will be added as the work progresses. For the vision component of the project, a simple depth camera was simulated, which is able to generate point clouds of the simulated environment. The camera is fixed above the workspace with an overhead view, which prevents any object from occluding another, while having all objects recognizable and distinguishable. Additionally, the fixed location ensures that anything that shouldn't be in view is not, reducing the potential for security risks. When simulating a real-life environment, it is important to be aware of possible collisions. To reduce the risk of the arm colliding with surfaces, Cartesian planning, which plans linear trajectories through waypoints, is used when interacting with the objects on the surface. The vision pipeline is composed of two main components, localization and recognition. To locate the object in space, the point cloud from the depth camera is processed and a pose of the object is found. An example of this can be seen in the image where the pose of the cube is estimated with respect to the world frame. This information is used to direct the manipulator in how to approach and grasp the object. Deep learning can be used to classify objects in the workspace. The ability to recognize different objects allows for them to be handled appropriately for automation tasks. This increases the complexity the tasks can have. In assistive tasks, recognition can be used to help determine the intent of the user through visual cues and to identify the correct object to manipulate. Locating an object from a point cloud means you have to isolate the points that make up the object from the rest of the cloud. An example of the original point cloud is shown at the bottom of the slide. When processing the point cloud, first a pass-through filter is applied which removes any points that fall outside a given bounding box. In this case, the surface where we are looking for objects is fixed, so the bounding box is placed to only contain that surface. The remaining points are shown in the second image. Next, any large remaining flat surfaces, identified using plane segmentation, are filtered out. This leaves only the points that correspond to the objects. At this point, the points for all the objects have been isolated, but the points are not yet associated with just one object. To distinguish the individual objects, Euclidean cluster extraction is used to group points that are close together into separate clusters. This allows us to isolate the points for just one object, as shown in the first picture where the cubes are filtered out, leaving just the cylinder. Finally, using the point cloud for just the object of interest, in this case the cylinder, the centroid of the cloud is estimated, giving the pose of the object. Now I'll walk through a demonstration of using the localization component of the pipeline with the robot. First, the robot arm is shown in a home position with the object on the surface. The left half of the image shows the gazebo simulation environment, and the right half is the visualization in RViz, where the point cloud can be visualized. From the point cloud, the location of the can has been found using the steps previously described. The robot plans a path from its home position to the position of the can. In the next image, the robot has executed that path and grasps the can. It plans the path to the drop-off point on the next table and begins moving the can. You can now more clearly see the white point cloud of the can that was used to estimate the can's location. The robot continues through its planned path and places the can on the other surface. Finally, the arm is returned to the home position where it waits for the next object. For the recognition part of the vision pipeline, I will be using deep learning. Deep neural networks have become more popular in recent years and are a powerful tool for tasks such as image recognition. Deep neural networks consist of a series of layers through which an input is passed, returning an output. In the case of a classification task such as the one I am working on, the output would correspond to the type of object. There are, however, some challenges with passing a point cloud through a neural net. Point clouds are unstructured since they don't fall on a grid like 2D images, which are a grid of pixels. Point clouds are also unordered, where you can list the points in any order and get the same result. This is unlike 2D images, where if the order of the pixels change, the image changes. They can also be sparse and irregularly distributed, where you can have more points in one area of the cloud than another. With these challenges in mind, I will be using a neural net based on the point net architecture. Point net can be considered the foundation for most neural nets using raw point clouds. The neural network for this project will first transform the inputs and pass them through a series of layers, including convolution, pooling, and normalization, and output scores for each class object. Deep neural networks require a lot of data to train on with enough variation that the trained model is robust to noise and generalizable to new data it hasn't seen before. Since it can be challenging to build a dataset from scratch, it can be useful to use an existing dataset which has similar classes of objects. For this reason, I will be using an existing online dataset, such as ModelNet, as well as a smaller dataset generated from my simulated environment. The reason the large dataset is helpful, even though it's less specific to the task, is due to the idea of transfer learning. Transfer learning is the idea that the neural net can learn more general relationships from the larger and less specific dataset, which can then be transferred to the smaller dataset. The general relationships are kept, while the specific relationships are adjusted to better fit the more relevant data. Common transfer learning techniques have two main steps. First, the neural net is trained on the large existing dataset. Then the general relationships you want to preserve, which are the trained weights and parameters for each layer, are frozen so they won't change. Finally, the network is retrained with the smaller specialized dataset, except for the frozen parameters which have preserved the general relationships from the larger model. As a result, we have trained a more generalizable and robust network with the small dataset than if the network had been trained on just the small dataset. Another area that would greatly benefit from the vision pipeline is cobotics, or collaborative robotics. Cobotics, in a glovebox setting where the robot is working alongside and assisting a human user, would require an additional visual interface for communicating with the robot. The user's movement can be limited in a glovebox, so possible interfaces could include recognizing basic hand signals or easy-to-move markers or tags. The markers could be used to tell the robot what to manipulate and where to move objects. While it could not be explored in depth this summer, cobotics is another area which, like automated tasks, would have improved flexibility and efficiency with the addition of robot vision. Thank you.